Hi guys, so now we're going to look at the gated SR latch, the gated set reset latch. If you haven't watched the previous videos covering introduction to sequential logic circuits and covering the regular ungated SR latch, I do advise you do so that you're able to follow along much more easily in this video. So we're going to cover the gated SR latch, why it works, why we need it, and how to analyze and properly solve problems concerning it. So now we're looking at the gated SR latch. To do this, I'll first of all draw the SR latch, the one we're familiar with. Okay, so you've got a NOT OR inputs leading to Q, then another NOT OR leading to NOT Q, and then the cool trick is that the outputs are fed into each other. Okay, this should be resets and this is sets. So this is my NOT OR, my NOR configured SR latch. So this is an active low, a normally low. Since I'm using, okay, I'll do another video to explain this. But since I'm using NOR gates, that means these guys need a binary 1 to change the states, and they use 0 0 means the state is maintained, 1 1 means the state is changed. So this means I'm using normally low configuration, which means active high. I'll need a high inputs, but this will be explained in another video just so we don't get confused. But just have this at the back of your mind that you can design SR latches with either NOR gates or NAND gates. This is going to be for the NOR gates, and I'll definitely do more explanation lectures on designing this with NAND gates. All right, so let's move on. We have the gated SR latch, and we've been able to establish in the previous lecture, that changing either a set or a reset is going to be able to toggle our output between 0 and 1. Leaving both of them as 0 means it latches on to the previous state and it stays the same. But we run into a problem. We have two inputs in this case, set and reset. So meaning that if any of these change, so if this was 0 and this was 0, and something randomly made this reset change from a 0 to a 1, then my output Q is definitely going to change. If something random made my S change to 1, then back to 0, and made this go back to 0, then my output Q is definitely going to be affected. So this is kind of a wonderful circuit, but we don't have absolute control of when my circuit changes. Okay, so that's the problem. That's why we introduced the gated SR latch. I need a way to assert, to show that, hey, whether or not things are playing with my SNR, as long as this condition is not met, nothing should happen to my output. So we'll now come to realize the real necessity of the gated SR latch. So how does the gated SR latch work? You start with drawing your regular SR latch, right? So let's start from this so we sort of understand what's happening. Okay. So this goes into our inputs here and here, coming out. Then, importantly, the feedback to each other. Okay. It's the most important. And then we could go on to write this as sets and resets, but we're going to do something much cooler. We're going to link these guys together to something that will affect their states at the same time. Okay, and for that we're going to use an AND gate. Okay, let's keep that straight. Okay, let's use an AND gate for that purpose. So this would normally be, usually would be our reset, and this would be our set. But we're going to make this the output of a NAND gate. Okay. And then the input for this is going to be coupled. Okay. Coupled together. And we have our gated SR latch. Okay. Yes, this looks complex, but let's walk through it and then see how it's actually pretty simple. This will still remain our resets. R for reset. This will still remain our set. But in this case, we're going to have an enable pin, okay, which we can abbreviate with E. Remember, these are AND gates, okay? And. So what's happening here? Remember the problem we ran into in the regular SR latch is that our bits could randomly change and then our output, and then our output would always be changing, is uncontrolled, is ungated, is subject to any change. But if I'm able to put a condition that makes this stick, okay, this enable, then I can control when my output is affected and when my output is not. So the enable can take two states, okay, 0 or 1, as with all binary inputs. And the whole purpose of this, as the name implies, is to enable my circuit, to activate my circuit. So far as my enable is 0, okay, so let's say I have 0 on my enable here, then I mean 0 gets fed here, 0 gets fed here. So whether or not my reset is 1, so let's say I wanted to, reset my outputs. So I have something on my output here, and I want to reset. So if I had set, reset, usually keeping set as 0 and reset as 1 is going to very elegantly clear the outputs, right? Keeping set as 1 and reset at 0 is going to raise an output. Output is going to be 1. Okay, let me stop drawing. Output is going to be 1. So what happens with the enable pin? It's something very much more peculiar. So with the enable pin now, we now have an absolute control of what changes. So if set is 0, okay, so let's put something on the screen. If set is 0 and reset is 1, and enable is 0, nothing is going to happen because enable maintains absolute control over my circuit. So let's follow that through. Enable is 0. So 1 and 0 is 0. 0 and 0 is 0. So that is what gets fed into our regular SR flip-flop. So this entire half is what you may call the steering circuit, okay? So this entire part, you can call it the steering or the control, okay? The steering circuit. Because it steers the direction UI. It steers the direction that the output is going. So the enable maintains control. So as long as my enable is 0, nothing can happen to my output Q. So we can follow that through. Okay, which other condition can we use? So let's say I want to set my outputs, right? I want to set my outputs. Initially there was nothing on the screen and my enable is 0. If I want to set this, okay, reset has to be 0. So set 1, reset 0, these come into the gate. And as long as I hope you can see it now, as long as my enable remains 0, the AND of this operation always gets to 0. Meaning that whatever is getting fed into my SR latch, so this is the latch circuits, okay? Whatever is getting fed into my SR latch is 0. And remember, 0, 0 for S and R maintains the previous inputs. So it's kind of like a super gatekeeper, a super doorman, a super gate man, okay? So it stands at the gates and says, hey, as long as enable, I'm closing this door, nothing can happen. As long as enable is opening the door, nothing can happen. So let's see if we can get around to drawing a truth table for this rather peculiar circuits, okay? So that we can be able to properly write down what's going on. Okay? Another question some people may fall into is, if enable is 0, does that clear the outputs? Like I said, no. Enable is not capable of clearing, it's not capable of writing. It's only able to allow states to be changed. All right? So let's draw the truth table. Let's do enable. Enable over here. Okay? S for sets. R for resets. Assume for Q at time t plus 1. Okay. And then we could write an explanation on afterwards. Yeah. So let's assume my enable is 1. So once my enable is high, then my entire circuit is allowed to come alive. All right. So let's say my enable is high. Okay. So we have 4 cases where my enable is 1, 2, 3, 4. My enable is high. Everything else now resembles the regular SR latch truth table that we're familiar with. Okay. So if enable is high and SR and reset are both 0, then I still have no change on my outputs. Okay. Recall from the SR latch video that if both SR are being 0, made no change on the outputs. We can follow it through here. 1, enabled is high, so that's 1 and 1. If these are 0 and 0, then 1 and 0 and 1 gets to 0. 0 and 1 gets to 0 here. All right, which means that whatever input was here, whether this was a 0, to get ignored with this, output fed here and still maintain 0. If this was a 1, to get ignored with 0, fed back and still maintaining 1. So all of this is just made possible that my enable is able to give me control over when this changes. Okay, so it's really useful in computing, in control systems, in manufacturing, and all that to prevent mistakes from happening. All right, so the circuit remains the same. If my set was high and my reset is 0, I mean, if I want to write something to my screen, then this sets Q to 1 because my enable is high. If my set is low and my reset is high, then it sets Q to 0, as the name implies. Okay, if sets and resets are both 1, then this still remains a forbidden input, because we were able to show in the video before that both of these being 1 means Q and not Q are able to be the same thing, which is not permissible in Boolean logic, in binary logic. Okay, so it's the exact same truth table you encounter. However, once my enable becomes 0, then my inputs of sets and resets don't matter at all in the slightest. Nothing happens, no change. So it still remains you can call it inhibited. Okay, so although there is no change, because there will definitely not be a change on Q. Although there is no change on Q, it is not because you're keeping your set and reset at 0. It is because your enable is preventing any further action from occurring. So that's all we have to handle with the gated SR latch. Next videos will definitely cover much more interesting concepts, why you may want to use something else other than enable. So if I want my circuits to come on every half a second, okay, I'm not going to be able to trust my hand to press, because you can usually think of it as a button. I'm not going to trust my hand to be able to press this every half a second accurately. So we introduce automated signals, clock signals, that now replace the enable inputs. All right, so these now form flip-flops. These form more complex sequential circuits. Okay, recall that this is one configuration of designing SR latches, which is the normally low that needs an active high input, that needs a 1 to change. All right, I'll get to covering this with the NAND, which is the active high, that will need a 0 to change. But nonetheless, this still stays the same. The logic is still going to be exactly the same. Remember, if you do have any comments, any questions, any mistakes you've noticed, anything you're not absolutely sure of that you'd like to point out, please do well to let me know in the comments or making a post on the channel. So thanks for watching. We definitely will get into more digital electronic concepts, and I'll see you in the next video.